So now what we need to do is look at the intermolecular forces. Intermolecular forces are the forces of attraction between molecules, and they can be very, very different. If you think about water, water is a liquid at normal temperatures because it has very, very strong intermolecular forces. Carbon dioxide, on the other hand, is a gas at room temperature because it has pretty weak intermolecular forces. So let's summarize the different intermolecular forces that we have. And there are three types. There's dipole-dipole, London, or sometimes called London dispersion, or sometimes just dispersion, London forces, London dispersion forces. And then there's hydrogen bonding. So these are the three types of intermolecular forces. So these are things that these are not bonds. Bonds hold atoms together within a molecule, but these are attractions between molecules. Okay, so let's start with dipole-dipole forces. What happens when you have a polar molecule, remember that a polar molecule has a positive end and a negative end. The positive end of one molecule will be attracted to the negative end of a neighboring molecule. So it's called a dipole-dipole force because polar molecules tend to align themselves positive end to negative end. So here's an example of hydrochloric acid. The negative end, because Cl is much more polar than H, the Cl end is going to be much more negative, not completely negative, but it's going to be more negative than the H. So that's what the delta is, a partial negative, and the delta positive is a partial positive. And then when you line up the molecules, the Cl, which is more negative, will be attracted to the positive end of the neighbor. And so there's an attraction holding those molecules together. Ionic compounds are actually an extreme, so they're not polar, they're actually ionic, and so we know that a positive and a negative ion are attracted to each other, and this is just a little bit less strong where the negative end and the positive end are more attracted to each other, but it's not a full charge. Okay, and this is sort of an example of these dipole-dipole attractions. A positive end is attracted to a negative end, and not just one to one. They're just they sort of make this kind of a meshy thing. And notice that in this case, the solid is held much more rigid than the liquid. However, there are still these attractions. It's just that the liquid has a little more energy, so they're able to pull apart and break those attractions a little easier, but still there are those attractions present. Now, hydrogen bonding is just an extreme type of dipole-dipole interaction. It's a special type. And hydrogen bonding gets its name, and it's a misnomer because it's not a true bond, but it is an attraction. A hydrogen bond is between a hydrogen atom of one molecule, and the hydrogen is bonded to either an F, an N, or an O. And if you look at the periodic table, we know that N, F, or O all have the highest electronegativity of all the atoms. So they're on the upper right-hand corner. So a hydrogen is very, very tiny, and the N, O, or F is very, very negative. And so what happens is you get a very polar molecule, and the interaction between them. So it's still a dipole-dipole interaction, but it's a very strong dipole-dipole interaction for two reasons. Because the negative side is very negative because of the high electronegativity. And the hydrogen is very, very tiny, and so it can actually get in very close to the negative end. And so they get in really close, and it's a really strong attachment. So a hydrogen bond is just a very special kind of dipole-dipole interaction, which is the strongest kind that we can have. And so here you can see, again, hydrogen bond is a misnomer because these are intermolecular attractions between molecules. A bond is then an intramolecular, within the molecule. But so here, if we have a hydrogen atom bonded to an oxygen, then we know that the hydrogen end is much more positive, the oxygen is much more negative, and because it is a dipole, but because the O is so electronegative, it's very negative, and the H, being very tiny, is very positive. And so we can then, the hydrogen on one is attracted to the oxygen on another molecule of water, and so this forms this hydrogen bond. So here's a picture of it. So the hydrogen is attracted to the negative oxygen, and then the negative oxygen is attracted to a neighboring hydrogen, and so forth. And so these are very strong attractions between water molecules, or not just water, ammonia, anything that has an N or F, but it has to be direct, the H has to be directly attached to the N or F in order to make a hydrogen bond. And this outlines what I was saying earlier. Because O, N, and F are the most electronegative, that end will be the most negative possible. And then because H is very small, it can move in very close and make a really strong interaction. However, again, keep in mind that these actual interactions are still weaker than covalent bonds. However, the intermolecular forces, these are the strongest of those. So these are stronger than regular dipole-dipole interactions. These are really, really important interactions biologically. What this is showing you is the hydrogen bond is what holds the DNA helix together. And this is a little bit of a, you can see on the left, the parts of the DNA. On one side, there's the NH bond, and it's attracted to an O. Or an N is attracted to an NH bond. So you can see that an H attached to an N, O, or F is then attracted to another O or N or F or something like that. So these are really, again, very important interactions in water, and the reason why water has such a high boiling point is also very important in so many biological. It gives the shape of proteins is because of hydrogen bonding, the DNA held together because of hydrogen bonding, etc. So these are really important attractions. Okay, and the last force is called a London force, and these are the weakest attractive forces. All molecules have London forces. It's just that some molecules also have dipole-dipole or hydrogen bonding, which become more important. So if something's nonpolar, the only kind of force they have are these London forces, which again are the weakest. And a London force is just an instantaneous dipole. So because these are nonpolar molecules and they don't really have a positive end or a negative end, but sometimes this is called an induced dipole because it will, for just an instant in time, because of electrons moving, one end will become more positive, one end will be more negative just for that instant. And so that creates an attraction between molecules that is not lasting. It doesn't stay very long. On the next slide, we'll see an example of what I'm talking about. But just keep in mind that London forces will increase with molecular weight. So a bigger molecule will have stronger London forces because they can be more distorted, which you'll see in a second. Any kind of molecule has some kind of London forces. It's just that some molecules may have also dipole-dipole or hydrogen bonding. So a lot of times those really dominate, but every molecule has some kind of London force. And London forces are also called dispersion forces. So this is a picture. What's happening in this atom? So neon is a nonpolar. It's actually an atom, not even a molecule. Neon is nonpolar because it's only an atom. But at some instant in time, more of the electrons may be on one side of the atom than the other, and so it creates an instantaneous dipole. So one end is a little more negative than the other. So what happens to a neighboring neon atom is that if that instantaneous dipole starts up, it will push the electrons on a neighbor away. So you can see the two neons here. The one end is negative. It will create a positive end. It will push the electrons to the other side, and it will create a sort of a temporary attraction between the negative end of one atom and the positive end of another. But it's instantaneous, and so it'll go away very quickly. And then the negative end of one will push away the electrons and create a positive charge. And you can see here that they kind of go back and forth because sometimes the negative end is on one side, sometimes it's on the other. But what happens, sometimes these are also called induced dipole, because if one is a little bit more negative, it will induce the next one to have a dipole, which will then induce the next atom to have a dipole, and down the line. Sort of, I like to describe it as sort of as the wave at a football game or whatever. One part starts it, the next part takes it up, the next segment takes it up, the next segment takes it up. It keeps going down the line. But of course, the first segment is already done before the last one gets it. So they're instantaneous attractions between atoms that don't last. And so that's what a London force is. You can check this little YouTube. It shows sort of a attraction between atoms or molecules that are nonpolar. Intermolecular, the term van der Waals force, that's another term used, is a term that includes dipole-dipole forces and London forces. So you may hear that term sometimes. So again, hydrogen bonds are the strongest intermolecular force. Dipole-dipole and then London dispersion are the weakest. So again, in summary, intermolecular forces play a large role in physical properties of liquids and gases, and also solids. Vapor pressure, surface tension, viscosity, the boiling point, not so much the freezing. The freezing point can be affected somewhat too. So again, the vapor pressure of a liquid depends on intermolecular forces. If intermolecular forces are strong, we have a low vapor pressure. If vapor pressure is low, then we tend to have a high boiling point. So for example, water has a very low vapor pressure because the molecules are really strongly attracted to each other. So they're not going to separate easily. So the molecules will not escape into the vapor very easily, which means it's going to take a lot more energy to boil that substance. The next little chart will show this idea. And so again, so we can look at this chart, and now you can't tell a whole lot from it. We haven't gone into it, but what you can see is the higher the vapor pressure, the lower the surface tension, the lower the viscosity. So they all go hand in hand. So they're showing you how water has a vapor pressure of 18 millimeters of mercury. So it's pretty low compared to, let's say, carbon dioxide, where it's 43,000 millimeters of mercury, much higher vapor pressure. Water also has a lower surface tension than carbon dioxide. Oh, I'm sorry, a higher surface tension. So something that has a low vapor pressure will have a higher surface tension and a higher viscosity. So you can kind of look at that. And some of these are really hard to tell. We'll talk a little bit more about this in just a second. So in the same way, viscosity will increase with increasing intermolecular forces because the stronger forces increase the resistance to flow. So there can be other factors connected to viscosity, like long molecules can tangle together, and so there can be other things just besides intermolecular forces affecting viscosity. Okay, again, the boiling point, the normal boiling point, is related to vapor pressure. And so the stronger the intermolecular attractions, the harder it is to pull them apart. And so the higher the boiling point. The weaker the intermolecular attractions, the easier it is to pull them apart. And so the lower boiling point is. So low boiling points for higher vapor pressure for weaker attractions. So if something has a hydrogen bond, they actually have abnormally high boiling points compared to other molecules. And so that's what comes on the next chart. So you can see water is the highest out of all group 6A hydride. So let's look at the chart. Okay, so you can see here that, and we talked real briefly, and we're going to kind of go over this again in just a minute, but you know, the bigger the molecule, the bigger the London forces, and so you would expect the stronger the attraction, and so the higher the boiling point. So if you look at this chart A, you can see that H2S has the lowest boiling point, is lower than H2SE because H2SE is a bigger molecule. H2TE is a bigger molecule. So you see the trend. You expect that the boiling point will go up as the molecule gets bigger because it has stronger London forces. So if water were a normal molecule, you would expect the boiling point to be even lower than -60. But because water has that really strong hydrogen bonding, it actually has that boiling point up above at 100. And you can look, if you look at chart B, you can see the same trend. So if you look at the lowest line, you see the normal trend. CH4 is the smallest, so it has the lowest boiling point. And then SiH4 is a little bit higher. GeH4 is a little bit higher. SnH4. So that trend goes higher and higher because the molecule is getting bigger and bigger, and so that London forces are getting bigger and the boiling point is higher. But again, because HF, NH, HN, and OH all have that hydrogen bonding, again, those molecules have abnormally high boiling points because they have such strong interactions. Even though they're smaller molecules, the hydrogen bonding makes them very high. So that's an important thing. So I like to take a little bit of time here. It's not really part of what we're talking about, but I like to talk about water as the miracle molecule because it's really an unusual. It has so many unusual properties that it shouldn't have, and again, it all has to do with that hydrogen bonding of the OH attracted to the OH in another another water molecule. So, for example, water is the only liquid substance to be found on Earth in significant amounts, besides petroleum. But petroleum is this huge molecule, so really water is a very unique. Liquid water is easily converted to a solid or a gas under normal conditions on Earth, so that's actually very unusual for a molecule. Water has several unusual properties that sets it apart from other substances and makes it very favorable for life. And so life would not exist if water didn't have these unusual properties. For example, its solid phase is less dense than its liquid. So ice floats, which is unusual. The reason it's good for life is because if ice sank, it would kill all the fish because water would start freezing from the bottom of a lake rather than the top. It will freeze out since it's less dense. Ice will layer a lake and in fact insulate it. Water also has an unusually large heat capacity, which I'll talk about in a minute. It has an unusually large heat of vaporization and very high boiling point, so it takes a lot of energy to make that happen, which is good for life. And it can dissolve many substances, including polar substances and ionic substances. And this is the reason why water has all these properties is because, again, like I said, about these strong hydrogen bonds that form. Okay, so why is ice less dense than liquid water? Well, when water is a liquid, hydrogen bonds break and reform and the molecules move past each other. But as the molecules slow down, if you cool it down and the molecules slow down, the hydrogen bonds become stronger. So these molecules lock into place. But because of the shape of the way ice freezes, because of the hydrogen bonds that lock into place, they form ice pockets. So you can sort of see the picture here that the ice forms these hexagonal little shapes here because of the shape of water. It forms these, kind of giving those little empty spaces. And so, in fact, fewer molecules of water will be per unit of area in an ice than in liquid. You can see there's many more water molecules in the liquid water in the same amount of space. And so liquid is more dense than ice. So why is that important? The low density of ice means it forms at the top of a liquid body of water rather than the bottom. So it actually insulates the water, keeps the cold air from coming in, and it limits further freezing, which means that the fish can still survive even if the top of the lake or whatever freezes, the pond. Now, heat capacity is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree. And it turns out that water has a very high heat capacity. So water has a high heat capacity, which keeps Earth's temperature moderate. It takes a lot of energy to increase the water by 1 degree, and so you can tell that actually if you're near the ocean, it moderates the temperatures a little bit more because of the huge bodies of water. And so temperatures on Earth's surface are conducive to life, because they do not vary widely compared to other planets. So it's the water that actually keeps Earth's surface temperature relatively constant. And then finally, the fact that water has such a high boiling point and a high heat of vaporization means that water is actually a liquid at normal temperatures, which is very unusual for the size of the molecule. So what are some other important things about water? The high surface tension of water and the cohesiveness of the water is responsible for capillary action in plants. So because of the high surface tension, the water is attracted to the sides of other the straw, for example. So you can see that the insides of the straw, and that's also the meniscus in a pipette or in a burette or something like that. It's because of the adhesion of the surface to the sides of the straw, and then because of these strong attractions between molecules of water, the inside of the water gets pulled along as well. But you can see that you've got sort of that meniscus, that curve forming because it's more strongly attracted to the straw on the edges. And then finally, water is a universal solvent. Because it is so polar, it can dissolve many other polar molecules, and then also it can dissolve many ionic compounds because the ions are attracted to the positive and negative ends of water. And because living cells are mostly made up of water, the fact that they can dissolve so many nutrients and other compounds becomes a very important part of water. So what if I asked you about, if I gave you two compounds and I said, let's see which thing has a higher boiling point, water or carbon dioxide? Which compound has a higher vapor pressure? Which compound is more viscous, things like that. How can we compare properties by looking at intermolecular forces? Well, these are some important points to remember. So again, remember that intermolecular forces, hydrogen bonding is the strongest, then dipole-dipole, and then London dispersion is the very weakest. So hydrogen bonding is the strongest, dipole-dipole, and then London forces. However, any kind of intermolecular force is still weaker than an actual bond, like an ionic bond or a covalent bond. So again, but still hydrogen bonding is the strongest, dipole-dipole, and then London forces. All other things being equal, and so we'll talk about that in just a second. So remember that London dispersion forces operate in all molecules, whether they're polar or not. So polar molecules have both polar dipole-dipole interactions as well as London dispersion. Hydrogen bonding, if something has hydrogen bonding going on, it also is dipole-dipole and London dispersion. So that comes into play. It's important. And then also remember that London dispersion forces increase with increasing molecular weight, because the bigger the molecule is, the stronger those, the more electrons there are to be sort of dispersed and to make them induce a dipole a little bit easier. And so a bigger molecule will have stronger attractions than a smaller molecule, all other things being equal. And then also a longer and less compact molecule will have stronger London dispersion forces than a more compact molecule. So we'll go over some examples in just a second. So we have to have some guidelines as to how we compare physical properties of different compounds. So the first thing you want to do is look at the two molecules in question. If they have comparable weights and shapes, that means they have approximately equal London forces. So a more polar molecule will have a stronger interaction. If molecules are different in molecular weight, London forces become more decisive, and so a heavier molecule has a larger dispersion force and stronger interactions. But you have to be careful, because if something's a very large molecule and London dispersion, and something's a small molecule but hydrogen bonding, you really can't compare apples and oranges very well using this method. So if I give you some examples, they'll either be very different in size but not polar, nonpolar, or they might be very different in polar and nonpolar but be similar sizes. So it's hard to this is not a hard and fast rules. They're pretty kind of generic. Again, hydrogen bonding being the strongest is usually the most important factor, so you have to recognize that first off. All right, so let's look at an example. List the following compounds in terms of decreasing boiling point. And again, I'm not going to try to mix apples and oranges, so there'll be some you'll probably be able to follow the rules pretty well. So first of all, we have to determine, okay, decreasing boiling point, how is that compared to intermolecular attractions? Well, we know the higher the boiling point, the stronger the attractions. So basically what we want to do is list these from highest attraction, highest intermolecular attraction, to lowest intermolecular attraction. So then what we have to do is look and see what kind of intermolecular forces each molecule has. And these are pretty straightforward here because they're small, but you may have to review chapter 10, where we're looking at polar bonds and how to figure out what a polar bond is by looking at electronegativities. You remember the upper right hand corner of the periodic table has the highest electronegativity, and then it decreases as you go to the left and down. Anyway, so if we look at these molecules, what do we see? And again, keep in mind, hydrogen bonding only happens if you have an HF, HN, or HF, HN, or HO. Then we have polar molecules if the two ends have very different electronegativities. And then we have nonpolar, generally if they're all the same element, first of all, or if they're just an atom, they only have London dispersion because they can't have a polar bond. So if we're looking at these examples, hydrogen atom or hydrogen molecule will have to be nonpolar because it's a bond between two of the same atoms. A CO bond is polar. You may remember that from electronegativities, but or from that chapter. If not, you go back and look at the electronegativities, and I may give you those so you can tell. There's a very large difference in electronegativity between carbon and oxygen, so that would be a polar molecule. HF is also polar, and we just got through saying that will create hydrogen bonding, so that we know that's the strongest kind of attraction. And then neon, being just an atom, can only have, again, London dispersion. So which one has the strongest attractions? It would have to be HF. So that would have the highest boiling point. So H2 and neon are both nonpolar, so those would be the lowest. So HF would be the highest, and then CO would be the next highest because it's polar. H2 and Ne are both nonpolar, and so you wouldn't necessarily be able to determine which one is greater, but now we know the London dispersion. The bigger the molecule, the stronger the London dispersion forces. So hydrogen has a molecular weight of 2 and neon has a molecular weight of 10. So actually neon has a little bit stronger London forces because it's bigger. Again, CO has a dipole-dipole interaction, and HF is hydrogen bonding. And so HF, so if we list these in order, the strongest are the forces that are hardest to pull apart, so they have the highest boiling point, and so HF would have the highest, and then CO, and then Ne, and then H2. Okay, so now let's look at another example. List the following compounds in terms of increasing boiling point. So be really careful, know if it's increasing, decreasing, and know what the term is. So increasing boiling point means weakest attractions to strongest attractions. Okay, so if you look at these molecules, and the reason why they're drawn out is to sort of help you see the shape of the molecule as well, and see that the dark blackish gray is carbon, the little blue ones are hydrogen, and the red ones are oxygen. So the first thing you should notice is that if there's an oxygen and a hydrogen bond, that's hydrogen bonding. So A has hydrogen bonding. B actually has even more hydrogen bonding because there's two OHs. C is all nonpolar because a carbon-hydrogen bond is nonpolar. And then D is actually also nonpolar because that's just carbon-hydrogen bonds. So probably the highest boiling point is going to be B because it's got two places where hydrogen bonding is occurring. A will be below that because it also has hydrogen bondings. C and D are both nonpolars, so those should have the lowest boiling point. And then because they're both nonpolar, now we look at size, and so D will have a lower boiling point than C. So if we're doing increasing boiling point, we would have to say D is the lowest, then C, then A, then B. Okay, so how about this one? List the following compounds in terms of increasing vapor pressure. So you want to be careful because remember vapor pressure is opposite of boiling point. So to have a high vapor pressure means you have very weak attractions, and to have a low vapor pressure means you have very strong attractions. So in terms of increasing vapor pressure, we're going to be starting with the strongest interactions to the weakest interactions. All right, so again, if you look at A, first of all, you might say, oh, there's hydrogen bonding because I see an N and an H, but be really careful because there's no H's attached to the N. So there are no hydrogen bonding. However, a CN bond is very polar, and so A is dipole-dipole interactions. B has hydrogen bonding because you have that OH there. So anytime you see an OH, you have hydrogen bonding. So in terms of A and B, B will be the strongest attractions and have the lowest vapor pressure, and then A will be higher than that. Okay, so actually B is the lowest and then A. Now C and D are both nonpolar, so they both have higher vapor pressures. But again, because they're both nonpolar, we look at size. And so D being smaller will have the highest vapor pressure, and C will have a little bit lower vapor pressure because it has a little bit stronger attractions. So B, A, C, D.